recording. I have now turned on the recording. We haven't talked about any physics yet, so people on the recording didn't miss anything. But I've now turned on the recording. I'm a bad person and will forget unless someone reminds me. So I'm doing production for a local performing arts organization that's doing kind of an online concert interview thingy, and I'm running Open Broadcaster Studio for them. And I almost hit start streaming and sent a whole bunch of video to the NYS Baroque YouTube page. But fortunately, we were on the right Twitch channel. So what was I saying? Yes, there will be an opportunity to take another quiz on this same material later in the semester, which has the potential to replace this grade if you want. Yes, Vic and Forrest's Baroque music, not played on the organ, but played on the fiddle. So what we heard before class, a classic Passacaglia Fugue in C minor by Johann Sebastian Bach. But that's kind of one end of Baroque music, and the other, this concert that I'm helping produce over the weekend is fiddlers playing traditional music from old and new Scotland and other places. So like a lot of people are typing questions. Let me answer those as I can. The maximum on the quiz was 110, not 117. Does something say 117 someplace? Crew 77, if you believe your extra question was not graded, like the extra credit was not graded, then email your TA. Is there a way to look at the graded quizzes to see what you did wrong? So most of the graders were annotating them as we went, like writing little comments on stuff. Some people did it in different ways. Some people did it with Blackboard comments. Some people did it by writing on a PDF. I know there are some of our graders who wrote on PDFs using a tablet and stylus and are going to email you stuff. But regardless, there are solution videos posted. I emailed out the links last night. I'll put them in the video library today that are basically how to do all the quiz questions. That brings up another point. One of the things that I want to do going forward is do video recordings of solutions to everything. So all of your homework, all of your recitation problems, we will do video recordings of. We don't have like, here is a PDF of the solutions, but we will make explanation videos, because the important thing isn't the solution, it's the explanation. So we will do those. So what I'd like to do is I'd like to do those. I'm going to be recording those, obviously. That's how you make those things. But it's very easy to also broadcast them and to record them live. So I need to figure out exactly how I'm going to coordinate that. But I got on a lark when I recorded the ones for the quiz. I hit start streaming, and people showed up on Twitch and started asking questions. So we will do that now. It may be 10 p.m. on a Saturday night, right? It may not be a time that's convenient for everyone to watch, because I have to do these things when I'm able to do them. But I'll give people a little bit of heads up when I'm planning on recording something, and you can pop in and watch and ask questions. Yes, Tongue Plash, that's exactly what I'm doing, is I'm using Open Broadcaster Studio for everything in our class. I have OBS in front of me in a little window right now. That's how everything gets to Twitch. It's Bridget says, what are the letter grades? Is it traditional letter grades? So the thing that 90% is an A and 80% is a B and 70% is a C, there's no act of providence that says it must be that way. That's just what many American high schools have chosen to do. Many of you who are from high schools not in the United States use different grading systems, and it's not the laws of physics that say that a 90% has to be an A. So what we're doing instead is 80% is an A, 65% is a B, 55% is a C, and so on, and that's for the whole class. So if you look at your quiz and you got an 85, that's an A. If you look at your quiz and you got a 70%, that's a B. Anything else anyone wants to ask about quizzes? Again, not everyone's is graded yet. We are convincing the TAs to do that as quickly as we can. Sidney, how does the extra credit factor in? There was a harder question that if you answered, you would get 10 more points. It would just add it. And if you got over 100%, then we just do math with numbers over 100%. We have the technology. We can do math with numbers over 100%. Ralphie88 has, oh, PogChamp is a snake now. Okay. So the next thing I wanted to talk to you all about, and this is going to be kind of well, we might have the second part of the conversation second. But I am considering, rather than doing 5 quizzes, doing 4 or maybe 3. What that means is, right now, the way the calendar is set up, we have this class, Thursday's class, next Tuesday's class, and another quiz. Because we're doing 5 in the semester, that's how the math shakes out, right? So the current plan is 3 classes and then 1 more quiz. Now, I usually do, rather than 5 quizzes in the semester, I usually do 3 larger exams. And the benefit of that is we're not always preparing for a quiz. We have more time to sort of let things breathe and kind of take a bunch of ideas and really synthesize them and look at larger segments of material. So if you all want, we can combine the next 2 quizzes into one. So rather than doing a 60-minute quiz 3 classes from now, and then another 60-minute quiz 3 classes after that, we can skip quiz 2, and then on the date for quiz 3, have an 80-minute quiz taking the entire period on all of that material. And that would be worth, the credit of those 2 combined. Could I get people's thoughts on that option? Would you rather have fewer quizzes that are worth more, or would you rather have more quizzes that are worth less? So people are saying no, and I don't know which one you're saying no to.
More quizzes, less.
Say again?
More quizzes, less content.
More quizzes that are each worth less is what you're saying? Okay. More quizzes worth less. So that's what people want. Okay. So I was actually expecting the answer to go the other way, but this is why I ask you. So the next one will be next Thursday. So what I'll do is I will it seems like people's people's views are mixed, right? Some people want to do more, some people want to do less. We will do a real poll. Now, I can't do a real poll spread over both Twitch and Zoom, but I can do a real poll on Blackboard. So after class, I will set that up, and we will do it. Yeah, this is not a real poll, right? This is you all basically doing a voice vote, and it seems like it's contested, so we will we'll do something real. We may even give people options, but that actually will make recitation hard, so we won't do that. Yes, Shane. All the examples from recitations we will be doing video explanations for. So I think that's all the administrative things we have to talk about. I'll send that poll out later today. Regardless, so things are going to get, we're all wrapped up now. We're going to be doing more substantive things as we go forward. Are there any other questions about admin things or course structure? So, homework 3. So we're going to be posting homework 3 later today. It will be due next Thursday, before the next quiz. It will be shorter and due next Wednesday if we're not doing that quiz. So, people, okay, Lumbo is asking the thing. So you'll either basically, you're going to have 4 questions on the next 2 quizzes. Do you want them in 2 different blobs, or do you want them all at once? You know, maybe actually it might be 3. We might do 3 questions 4 weeks from now, or do you want like 2 questions next Thursday, and then 2 more questions 2 Thursdays after that? Those are kind of the options. So what is on these? What will be on these quizzes is use of Newton's laws to study how things move, which is what we're going to start today. The plan is, so let's kind of split up. Let's talk about how we're doing things going forward. So what we have done so far is we've studied what it means for an object to accelerate. So what we did is we said, all right, I know the acceleration as a function of time, and using kinematics, I can find its velocity as a function of time, or its position as a function of time. And all these little arrows just mean these quantities are vectors, and we can do mathematics with them like we do with vectors. So there's drama in Twitch chat. Yep, thank you, Adam. Adam just banhammered a spammer. Good job. This is why I didn't pay you, Adam. Also because you're good at teaching physics. So we saw that if we know an object's acceleration, we can use kinematics to figure out how it moves. But how do we know an object's acceleration? Why did we start this way? By saying, we know an acceleration, let's try to understand position and velocity later. And the reason is, we know Newton's second law connects the forces on an object to its acceleration. So, why am I starting with Newton's second law? Well, we'll come to that later, but for now, let's just do this. So, Newton's second law tells me that the sum of the forces acting on an object, added up, relate to its acceleration. Now, annotate this. Get out of the way in a minute. So this is the thing, this is kind of the obvious, what do the symbols in the equation mean? But this obscures what is really going on, because there's a cause and effect in here that is kind of being hidden. And it's always a good idea when you're thinking of the laws of physics to ponder what the symbols in the equations mean and translate them into language. So another way to think of this, and a way that is probably more illuminating, is instead to say forces cause acceleration. So if I apply a force to an object, I make it accelerate. One way, if I take this expression and I rearrange it, I could also say that this is true. We'll color code this a bit. So how would I interpret this? I would say the vector sum of the forces on an object well, actually, let me just rewrite this. I want to phrase my sentence slightly differently. I'll say forces acting on an object make it accelerate and I'll get out of the way in a minute. The acceleration caused is the vector sum of the forces divided by its mass. So what this means, basically, is if you push on stuff, the stuff accelerates. And the harder you push, the faster it accelerates. But the more massive the object is, the slower it accelerates. So these two expressions of Newton's second law mean the same thing, but this one over here kind of makes clear the cause and effect. That the acceleration that results from a force is equal to the size of the force divided by the thing's mass. And since these are vectors, the acceleration that results is in the same direction as the force. So I'm going to erase the board now. Why did we start with Newton's second law? That's actually an interesting piece of history. Newton's first law, anybody remember what Newton's first law is from high school physics? Inertia, an object at rest, O and W, vector sum of forces is 0. Never took physics before, that's fine. So, I just want to get in the corner of my board here. Newton's second law is sum of the forces equals mass times acceleration. But Newton's anything that can go wrong will go wrong. So Emarin has quoted some text. If a thing is at rest or moving at a so let me just read what Emarin has said. If a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at a constant speed unless it is acted on by a force. So that's a whole lot of words, and I'm not going to write them all up here. But Newton's first law, well, what is all this about being at rest or moving at a constant speed in a constant direction? That just means not accelerating. If you are at rest and staying at rest, or if you are moving at a constant speed in the same direction, you are not accelerating. So Newton's first law just says if the sum of the forces on an object is 0, then the acceleration is 0, too. Now, you might say, well, all right, that's obvious from here. Newton's first law just says, if this is 0, that's got to be 0, too. Why then did Newton make a big deal of this? It's because nobody appreciated that before. Historically, in the way that many people used to think of mechanics, in particular the Greeks like Aristotle, that people in Newton's time greatly admired, Newton's time and place, Aristotle thought you had to keep pushing on something for it to keep moving, and Newton's like, no, 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 no. It will keep moving on its own, you don't need to push on it. But Newton's first law is entirely contained within Newton's second law, so we're not going to talk about it anymore. Let's look at some examples of doing things with Newton's second law. To do that, we're going to need to know how to measure forces. So Aristotle wasn't stupid. Aristotle did a lot of work on other sorts of ideas, other kinds of philosophy, like moral philosophy. He really wasn't, natural philosophy wasn't really his key shtick. But he also, Aristotle's descriptions of motion are actually correct for a thing moving in a fluid with high viscosity, like a boat moving through water. So what Aristotle lacked was a framing of universality, of saying, these things that I am saying are true everywhere for all objects. When we talk about the process of science and the history and philosophy of science a little later in our class, we will get into that idea a lot. So to do any calculations with Newton's second law, we need to know more about force. So the things we're going to talk about now are what are forces, and how we measure them. So, what are some forces that you know about? They are physical pushes and pulls. So I often joke with students that a force is anything you can send that can send you to the hospital. If you fall on the ground and bang your face on the floor, that can send you to the hospital. That's a force. If you lean on the blackboard, so I'm leaning on the board, that's a force. The board is pushing on me. I can pull on things with ropes. I can blow on things with wind. I can attract things with a magnet. People have mentioned gravity, friction, a normal force. J-Dub says buoyancy. So tension, which is what you do with ropes. So physics is cool in Twitch chat has said normal force. We'll come to that in a minute. That just means pushing on stuff. Slapping people. One thing I want to note, so folks said gravity times mass. Yeah, mg is the formula for weight. Other ideas like people have said torque, jinx, moving in general. So vacant forests has brought up the really good point that I want to say. They've said, is momentum a force? Momentum is a thing. We will study momentum, but it's not a force. Forces are not abstract ideas like velocity or acceleration or the net force. The net force is not a force. Forces are, they are physical pushes and pulls, like the examples people have given me. So, gravity, tension in ropes. We will pull on things with ropes a little bit later. The force of handprints on a blackboard is incredibly powerful. Friction rubbing your hands together to stay warm. What are some other examples people gave? Magnetism, buoyancy, in our class, we're going to focus on ones that are mechanical. So in our class, we're going to talk about gravity a lot, we're going to talk about tension a lot, we're going to talk about friction a lot. Ideas of magnetism and buoyancy are going to need to wait until we study electromagnetism. Like that'll wait till physics 2. And Rebecca Andino has said there are different kinds of friction. Squatch has said that there are nuclear forces. Yep. Other people have mentioned the force. How is the force like duct tape? Star Wars fans? Duct tape is exactly like the force. It has a light side, a dark side, and it binds the galaxy together. Yes, Shane. We're not going to talk about midi-chlorians. So forces are physical pushes and pulls, things you can touch, things that can push on you. But forces are not abstract math ideas only. So examples of things that are not forces might be velocity, momentum, acceleration, the net force. Net just means add. Centripetal force. So we will talk a lot more about rotation later. But centripetal is a direction, not a force. So why am I sort of belaboring this? This next segment of our class is the simplest. And what do I mean by that? I mean that there is a simple procedure for basically understanding anything that we will do in the next unit. The challenge, so often when I see students make mistakes, they are making mistakes because they've added complexity that isn't really there. Yes, someone said movement is not a force, yeah. So often when I see students doing exams for this material, for like looking at the forces that act on objects, the mistakes they make involve making up forces rather than forgetting them. So like concocting things that don't actually exist and you allowing those to overcomplicate their thinking. So these are what forces are and are not. Now we need to talk about how to measure them. There is a discussion of centrifugal force in Twitch chat. That will wait until we deal with spinny things in a couple weeks. It turns out centrifugal force is a unicorn or a fairy. They don't actually exist. It's sometimes nice to pretend as though they do, and fairy stories are very valuable to our world. Mythology is very valuable to our world, but hobbits aren't real. And we will talk more about Hobbits and Centrifugal Force in a couple weeks. I may play a song about unicorns at the end of class. So, who took your teeth? Yes. Yes, the tooth fairy is very real. So how do we measure forces? Did this. So if force is going to be mass times acceleration, what units or what dimensions are forces measured with? Marin has said newtons, but what is a newton? Remember all the stuff we did at the beginning of the term where you can look at an equation and determine what dimensions something must have just by what's in that equation? So what dimensions must force have?
Kilograms per meters over second squared.
Yeah, exactly as she said. I'm going to push a button just to... So I now have something running, so anything the microphone hears, I hear in my earpieces, so I can hear you all better.
Okay.
I have like a monitoring thing going. So what she has told us is that, well, let's start with the one thing we know. Mass is a mass, and acceleration is a length per time squared. So that means force must have dimensions of mass times length per time squared. And conventionally, the units we would measure it in are kilograms meters per second squared. Now, we get tired of saying kilogram per meter second squared all the time. So, in honor of Sir Isaac, a kilogram meter per second squared, which we're going to get real sick of saying, is called a newton. A newton is about the weight of an apple. It's about 1/5 of a pound. So, I don't know, like this empty, fantastic owl mug, which actually, come to think of it, was a Christmas gift from one of our former coaches. The same coach who threw a boot into the stream gave me this for Christmas. Weighs about a newton. Yeah, my dad loved fig newtons. He would like get huge things of fig newtons and eat them when I was a kid, along with Chips Ahoy chocolate chip cookies. Yes, it is adorable, Mia. So this is how to measure forces. Let's do some simple sorts of problems. The first thing we'll ask is, we're going to kind of go one by one and study these forces that we have. The first one I'd like to talk about is weight, just the force due to gravity. So before, we talked about free fall. We saw that if I take two objects, even if one of them is light and one of them is massive, I'm trying to find a massive, convenient massive object that's pretty durable. Here we go. We'll use a piece of chalk and my keys. So both of these objects have very different masses, heavy keys, very light little piece of chalk, and if I drop them, they hit the ground at the same time. They didn't fall enough that air resistance mattered that much for the chalk. So we observed before that any object freely falling accelerates downward at g. So from before, any freely falling object accelerates downward at g. But why? Well, that is a tough question. At some point, we have to just say, that's how gravity works in our world. Can I drop them, then catch them before they fall? No. Would you like me to do this with a billiard ball and a feather? Because we can do that in class. We can bring a billiard ball and a feather. But in here, air resistance would mess up the feather, so we'd have to take them to the moon. Should we do class from the moon?
Yes.
You want to go to the moon?
Yeah.
All right. We can travel to the moon maybe next Thursday. I think we have Wi-Fi on the moon, and we can broadcast from the moon, but if not, we will figure something out. We'll try to get you Wi-Fi from the moon. I'm just going to push some buttons to make the picture better. There we go. The board will get out of focus less now. So, freely falling here means no forces other than gravity. So, we know that the sum of forces equals ma. We know nothing other than that. And if we were to think about the forces acting on an object, well, the only force is the weight force pulling a thing down. So let's put that in. I know the force of weight equals m I'm just gonna dispense with the vector sign here and say that this is downward. And this is pretty simple since I know the acceleration is g downward. So in one line, I've now figured out how hard gravity pulls on things. It pulls on things with an amount equal to the mass of an object times our constant g. Now, this is a big transition, especially people who have never taken physics before or who have taken like Regents level physics before. This is important. Before, up until now in our class, we have treated g as an acceleration. So we'll do a sidebar here. This is a very important kind of shifting of gears we're going to need to make for people who are new to studying physics. Before, we thought of g as an acceleration for freely falling things. But now we're not going to deal only with freely falling things. Now, not everything accelerates downward at g, because we're not just going to be throwing things and dropping things, we're going to be doing other stuff with it. So now, mg is the force of gravity on objects. So yes, g is still the same quantity. It's still about 9.8 meters per second squared, or 10 if you're lazy like I am. But we're no longer going to be saying, oh, the acceleration is g downward, because we're not going to be dealing only with things in free fall now. So make sure that you're mentally okay with this paradigm shift. That g is now going to appear as part of mg, which is the force due to gravity on objects. So that's gravity. All you need to know about gravity is it pulls downward on everything with a force equal to mg. What about in space? We'll hang on a few weeks. We're going to do that. One other force I need to talk about before we do a little bit of mathematics is something called the normal force. Now, you're probably thinking, well, is that like the thing that's not an abnormal force? Well, a normal force is a force that stops objects from moving through each other. So, is there a normal force acting on me right now? Yeah, Imaren says, is that what keeps us from falling to the center of the Earth? And Sad Ferret Boy has pointed out that the word normal in mathematics means perpendicular to. So I'm going to kick some things out of the way. I have like a table full of junk. So I have a comb. It gets caught in my hair and I tend to break these, so I can't. My hair and stuff. So if I'm just using this as a table, we're not going to need the thing that's on it. So you can now see that table. If I set a box on the table, well, why doesn't the box fall through the table? Well, as people said, the table exerts a normal force upward on the box. I could then set other things on it. I could say, well, the owl exerts a normal force on the box exerts a normal force on the owl. All of these things are pushing on each other, and we will see in a little bit how to understand those forces. But the short version, all you need to know now, is a normal force is objects in contact pushing directly on each other. Owl and box will return at the end of the class. I wonder what's in the box. This just came today. It's something I've been waiting for. In my box is the thing that I have needed, more chalk. So now I have an entire rainbow full of chalk, and now we can write in purple. Total PogChamp, y'all. Purple chalk. This is amazing. This is the best day of my life. I now have purple chalk. I need to get out more, don't I? Okay, I want to interrupt with something. Give me just a second. I may have a request for you all. Okay, serious talk, non-physics serious talk now. Mario Olivares, our head TA. Some of you have worked with him, some of you are in his recitations. Mario is an amazing person, and he's also a dog lover. And he has taken in a dog that he's taken care of for somebody else, and this dog is sick. So if you're in Mario's recitation and he hasn't graded your stuff, this is because he's been trying to help his dog survive. So Mario's email, which I'll put on the board, is this. So Teddy, the dog in the problem, is fine. Teddy is still like chewing on stuffed toys. But Mario's other dog, Brenda, is ill. So if you have a moment, drop Mario an email and just let him know. Send him get well cards for Brenda. I'm going to send him one as soon as I get out of class. So make Mario's inbox explode with get well cards if you are so inclined. I don't know about Kiki. I haven't seen Lindsay in a while, but I imagine Kiki is still jumping around and murdering things. She's trying to reach the elevator button.
Still?
Yeah. Yeah, I need to chase down Lindsay and ask her how Kiki is doing. If you want your cat or dog to appear in a Physics 211 problem, send me their name and what they like to do in a picture, and your cat or dog or pupper can also be famous, just like Kiki. All right. So I'd like to now talk about how we analyze problems involving forces, how we deal with objects that are moving under the influence of many different forces. Can your dog be a quiz question? Yes, send me a picture of your dog and what your dog likes to do. We had a final exam one year that was entirely people's dogs and cats. And I am super happy to do that. So I'm going to pose a problem. I'm going to say a cyclist rides at 5 meters per second at a, we'll just say, constant on flat ground. What can you tell about the forces on them? And we will change things about our cyclist as we go. We also should probably say, let's make our cyclist have a mass of 100 kilograms. So whenever you have any problem, the first thing you should start doing is thinking about what forces act on the object. Yes, Yulin, exactly. What forces act on the object? And Crew has said the forces are all balanced. So what we mean by balanced is they add up to 0. So let's make a catalog of these forces. What forces act on our cyclist? And Ian Storrs has said, draw a picture. The Pizza Man has said, draw a force diagram. I'm going to break out the purple chalk and draw a force diagram. So a force diagram is a very, very reduced cartoon of forces acting on something. In a force diagram, you draw the object as just a dot, and all of the forces as arrows pointing away from that dot. Okay, so Kelly Williams has said the force of the flat ground pushes the cyclist up. Let's go one at a time. We learned a term before for forces of an object pushing on something else that it's directly in contact with. What is that, Kelly? The normal force, yep. Switch colors, actually. So there is a normal force up from the ground. And I would draw that like this. What else? We have gravity is pushing down, says Kelly. All right, you ready? First use of the purple chalk. The weight pulls down. Now, this is a place where labeling this arrow, my preference here is to just write mg. I already know how big this force is going to be. So when you draw a force diagram, if you already know the size of something, label it with the algebraic symbol you will use for it. So here I know that I'm going to be representing this force with mg algebraically, so I can go ahead and put that in. But some people would prefer to label it with a w or even f sub g. All of those are fine. People have pointed out that there is a smudge on the lens. There's a speck of dust, 1 foot. Yeah, oh, you found it. I was hoping nobody would. There is actually a piece of dried liquid on the CCD of my sensor itself. Cleaning those things is very delicate, so I am waiting until the end of class to risk my camera's sensor to fix it. So here's a bit of photography. The higher the aperture I go to, the more flagrant it is. So you'll be able to see it there right under the word weight. So I'm I'm at f16 now, you can really see it. If I go even higher, it gets really, really, really blatant, right, under the word weight. So you caught me. I have a dirty piece of junk on my camera sensor. I will get it fixed when I can. But if I get it fixed now and break my camera, then we'll all be sad. Oh, you lose sound. Oh, am I broadcasting from the wrong mic? I probably am. That's really weird. Oh, so something is funny about how OBS is handling my audio. Huh. Yeah. Well, I'll get it fixed later. Some tech stuff is messed up on my end. So here are two forces on our cyclist. What else is acting on them? Well, so people have said friction and applied force. All right. thing that we're going to do differently than high school physics classes. So high school physics classes are fond of the term applied force to mean just a force that comes from outside. I'm fixing the camera a little bit. But here, rather than just waving our hands and saying applied force, I'd like to name what those forces are because we're going to need to think about them. So if she is on her bike, what will we call the thing that makes her bike go forward? What thing pushes your bike? What'd you say? Yeah, so you're pushing on the pedals, but you push down and the bike goes forward, right? So when we're going to study the physics of the transmission of a bicycle later, your massive quads make it go, yeah, traction from the wheels, right? So I rode my bike in today. And it is garbage weather in Syracuse. So in order to get enough traction to make the bike go, right, we have to have big chonker tires with things to give me more traction. So, and yes, this is one salty boy. I need to clean this thing so badly. Now I need to get it out of the way without knocking everything over. But this is why we have studded tires in the winter, right? Is bikes don't go because of a magical applied force. They don't go because you push the pedals down, at least not directly. They go because of traction from the wheels. So there's only one wheel that's driven. And which way does that traction go? Careful. So remember, which way am I trying to go on a bike? Forward, yeah. So we'll decide that this way is forward. You can label that track for now. We'll study what traction is a little bit later. There's one other force that I would need to worry about, which someone named was air resistance. Which would go backward. So this here is kind of our canonical example of a force diagram. Well, we believe in air. I was riding home riding back to where I'd parked my car at a little bit after midnight yesterday, and the wind was like, well, it was going against me coming in, but behind me on the way back to my car. And yeah, you notice the air when you're on a bike. People talking about. So Firecracker said something about why the back wheel is bigger than the front. They're actually the same on my bike. I was holding it up with the back, like one wheel closer to the camera. But yeah, the two tires are the same on this bicycle, but they don't need to be. There are bicycles that have unequal wheels, but they're equal on mine. Yeah, the wind was crazy yesterday. Okay. So Beckmunch has just brought up a really good point. Why is traction forward? We usually don't talk about this for a little while in our class, but we will now, because it's a good idea of a good demonstration of Newton's third law. So we'll come to that in a minute. I just want to make sure everybody is clear on this being how one draws a force diagram.
draw a dot, and then pointing away from that dot, draw all of the forces. Dexter asks, could friction and air resistance be described as the same? Air resistance is a kind of friction. Usually when we say friction, we mean the rubbing together of two solid objects, which we'll study in detail actually on Thursday. We will rub objects together and look at the frictional forces they apply. So Luke has said, what about the frictional force of the two things in contact, of the wheels in contact with the ground, which is the normal force times the coefficient of friction? That's a little bit trickier when things are rolling. Rolling motion is actually one of the harder things for us to understand in this class. So Luke, I'll defer your question until we talk about rolling things, because that's actually where we end the semester is understanding rolling. But it's a good question, so keep that in the back of your mind because we will come back to that. So let's talk now about traction, because it's a really good example of Newton's third law. How does traction work? Well, so if you think about a bicycle wheel, think about what you're doing when you ride your bike. You are pedaling the thing so that the back wheel pushes the ground backwards, right? So I'll probably knock some things over if I get my bike up here again, so I'm not going to do that. But you try to turn your bike wheel, and you are pushing the ground backwards. Okay, when you push the ground backwards, what also happens? Yeah, E. Marin in Twitch chat has alluded to Newton's third law in saying it pushes back. The ground pushes you forwards. Only the fanciest purple chalk for the big ideas. This is Newton's third law. So, what do you all know about Newton's third law? Michael Kelly has said equal and opposite reaction. It's Crew has given a great example. I don't come from a part of the world with that many boats. Well, Alabama has boats, but we never had them. In Arizona, we had more cacti and rattlesnakes than boats. But yeah, that's an even better example. Think about what you're doing if you're in a kayak. You get in the water, you put your paddle in the water, and you push the water backwards. And the water pushes you forwards. Yeah, and AZ561 says if you don't have a paddle, you can just do it with your hands. You push stuff back to move yourself forward. That example of paddling a boat is the best example. I've used people walking before, but yeah, paddling a boat's a great one. So Newton's third law says anytime one object pushes on another object, that other object pushes back with an equal force in the opposite direction. So what I'd like to do now is, in our last 10 minutes, I've got a simple example I'm going to do involving actually we'll do it with our erasers. How about that? So what I'm going to do is I'm going to just put my two erasers here. I don't even need the table. I'll put them in the chalk tray. So I'd like to ask, what are all the forces on these erasers? I need to use one of them to erase the board. And we're going to kind of go through a prototype of how to look at these problems. Don't worry, we have plenty of practice upcoming. Jilly Jewel says that they've been having network trouble. Has anybody else on Twitch had network trouble? Y'all are fine? Okay. I think we're fine, and the Zoom broadcast is actually a screen share off of Twitch. Yeah, I might be able to help with your network problems if you're having network problems. I just want to make sure that it's not afflicting everyone. I'm going to move this over. So here's our cartoon. We have big eraser on the bottom, which we'll label as A, and little eraser. Oh, I broke my first piece of purple chalk. Damn it. Press F to pay respects. And A will be our big eraser on the bottom. So what we'd like to know here are what are all the forces. So this is an example of a problem with more than one object. So there is a three-step problem-solving approach that you can use for all of these problems, which you will practice tomorrow, Friday, next week. The first step is always to draw a cartoon plus force diagrams. You can't calculate anything unless you have a clear accounting of what you're calculating, what forces there are. So we're just going to think about the two erasers here, which I'll put over in this part of the chalk tray. We're not going to worry about the chalk tray. We know it can't move. It's bolted into the wall. So what forces act on top eraser, on B? Did you all say something? No. Gravity and the normal force from eraser A. Yeah, so let's see. Gravity will be purple. So here, I've got two different masses. I have whoops. Write that in purple. So I need to use a subscript here to make clear which one I'm talking about. And there's also the normal force from A. We'll do in green. And I'm going to write this as FAB, which is the normal force from A on B. Okay. So now let's think about the forces acting on eraser A. What things act on eraser A? Say again?
The normal force of the thing there.
Yeah, the normal force, oh, I picked it up. The thing on pushing down on it, right? Yeah, so I also have, we'll do this one in white, FBA, the normal force from B on A. What else do I have? Yeah, mg. Oh, so Miles has already started calculating. Here is, we will come to that in a moment. And we're almost out of time, so I'm going to go a little bit faster. We've also got the thing's own weight. Right, so mAg, the weight of eraser A. And then finally, we've got the force from the chalk tray pushing it up. We'll say this is the force of the tray acting on A. Now, so Beckmunch has said, what about the length of the arrows? Yeah, if you know which forces are bigger and which forces are smaller, then go ahead and draw the arrows different lengths. This is especially helpful when you're adding vectors, but you don't need to. You can always just draw them the same length. Algebra will tell you what's bigger. So what do we do now? In our 3 minutes left. The next step is write down the sum of the forces equals ma for each object. And you can always just read this off of your force diagram. So for instance, for this one, if we choose up to be positive, I can say FAB minus MBG equals MBA. And for this one, again, just read it off the diagram. The arrows going up are positive, the arrows going down are negative. F table on A, or tray on A, minus MAG minus FBA equals MA acceleration. So this is the second step. First we draw the diagrams, then we write down Newton's laws. And then finally, so here I've got lots and lots of symbols, but are any of these forces that I have written up here Newton's third law pairs? Yeah, Porpoise has said that FAB and FBA are equal. This is a direct application of what Newton's third law says, which is that if A pushes on B, B pushes on A with an equal force in the opposite direction. We've got that in our diagrams, right? This one goes up, that one goes down. You're going to do this in recitation tomorrow for 3 objects, and then do the algebra to calculate the forces. You'll know, for instance, that the accelerations are all 0 here because nothing is moving. We're out of time. We spent a lot of time kind of talking about plans for quizzes at the beginning of class. I will survey you all on Blackboard. That'll go live today, and we'll make a decision tomorrow about what the schedule will be. Because it's in the syllabus to have 5 quizzes rather than 3, it will require a supermajority to change. We may have options for people. We will figure that out as we get closer to time. So we're out of time. Are there any questions for me? Anything anyone would like to talk about? Of course, you all can hit the hang up button anytime you want. Porpoise has said YMBG boop, plus MAG. Boop. So it seems like So what I will say, folks, is in this sort of thing, you always wind up solving the system of equations by substitution. You will be calculating one variable, plugging it in, finding another variable. You will be doing a ton of that in recitation tomorrow. Oh, Adam reminds me that we have more space in in-person recitations. We likely have enough space to accommodate anybody. Dexter, please hang on a minute. So if you are here and you would like to go to in-person recitation and have not yet been doing that, please send me an email. I'm going to try to get to those very, very quickly and verify that you have a spot. But I'll send out a note about that soon. Dexter, when you say what is the last time to get a grade, I'm not quite sure what you mean. Do you mean for the quiz? So Dexter, did you do the quiz last Thursday? So if since you're here and you're inquiring about your grade, I obviously can't grade your quiz on stream, right? That's not cool. But if you send me an email, like just so I know your name, I will take a look at your quiz and I can get you a grade right away since you're asking about that. I can grade that like right now. Beck Munch said, "Are you allowed to drop the lowest quiz?" Yes, you will always be able to drop the lowest quiz grade. Rebecca Andino says, "Is FTA?" So this is the force of the normal force of the table on A. If these things were sliding, we would have friction. We haven't studied friction yet, so there's no friction yet. We will be adding friction later. Thank you, NJS. Thank you all for showing up in person. I have to figure out what's going on with my computers. On the last part of the second equation, does it say, yeah, so this is the mass of eraser A times its acceleration. Yeah, so mass of A times acceleration, and we know all of that's 0. Yes, the lowest quiz grade will still be dropped. Usually we drop the lowest of 3. This year we were planning on dropping the lowest of 5. Later. Thank you all for coming by. Yes, Imaran, they will be worth more since there are less of them. So if we do this, we will be combining quizzes 2 and 3 and into 1 at the date of quiz 3, and it'll be worth double. I will send you all a survey with more information. CJV, yes, your lowest homework grade is not counted. Yulin asks, why are these terms why are these terms 0? No. The acceleration is 0 because nothing is moving. These erasers are just sitting here, so you know their acceleration is 0. We ran a bit short on time there because I got sidetracked by some other things, but you will have lots of practice tomorrow in recitation. I'm going to hang up the stream now. I will be having my normal clinic hours from 1:30 to 3:30 today when I can help anybody with anything. I will see you all later.